Hello everyone, welcome back to my VLSI Diary. My name is Shivangi Upadhyay and in today's video, we are going to understand two very important timing concepts in digital circuits, combinational delay and contamination delay. These two delays are very important when we talk about timing analysis, but many beginners get confused between them. So, in this video, I will explain both concepts in very simple and clear way with proper examples and visual understanding. By the end of this video, you will clearly understand that what is contamination delay and what is combinational delay, the exact difference between them, and most importantly, where these delays are used in real VLSI timing analysis. So let's start. Let's start with the first concept, which is combinational delay. Combinational delay is the time taken for a signal to travel through combinational logic from input to output. It is the total delay between input change and the final stable output. Now, let's understand this in a practical way. When input changes, the output does not change instantly because the signal has to pass through multiple logic gates. This entire time taken is called the total delay through logic. In real circuits, data does not pass through just one gate. It passes through multiple gates. Each gate introduces its own delay, like gate 1 introduces 2 nanoseconds, gate 2 introduces 3 nanoseconds, and gate 3 introduces 5 nanoseconds. So the total combinational delay is equals to 10 nanoseconds. Total delay is the sum of delays of all gates in the path. Now the another important point is combinational delay depends on how many gates are in the path. Like more number of gates means more delay. This is also called the logic depth. Delay is not same for all gates. It depends on the type of gates, technology used, load connected to the gate. So real delay can vary depending on design. When input changes, output may fluctuate initially, but after some time it becomes stable. So, this final stable time is defined by the combinational delay. Now, why it is important? Combinational delay is the major contributor to total timing delay in the circuit. It helps determining the critical path and ultimately decides the maximum operating frequency. In a timing path, flip-flop launches data, combinational logic delays it, next flip-flop captures it. So combinational delay is the main delay between two flip-flops. Combinational delay defines how long a circuit takes to produce a stable output. Now that we understand combinational delay, let's move to the another very important concept, contamination delay. It is the minimum time after which the output starts changing when the input changes. It tells us how quickly the output begins to respond, unlike combinational delay, which is the total delay. Contamination delay represents the minimum possible delay in the circuit. It corresponds to the fastest path between input and output. When input changes, output does not wait to become stable. It starts changing after a small time. That initial change is defined by the contamination delay. Contamination delay marks the beginning of the output transition. Some important points are at contamination delay, output is not stable yet. It may still be transitioning or even incorrect temporarily. It only tells when output starts changing, not when it becomes correct. In a circuit, there can be multiple paths from input to output. Contamination delay is determined by the shortest or fastest path. Usually, fewer gates equals to smaller delay. Because output starts changing early, it creates temporarily glitches or unwanted transitions, especially in complex circuits. Now, why is contamination delays important? It is very critical for hold time analysis. If contamination delay is too small, data may change too early and violate the hold time. In a timing path, contamination delay is equals to the earliest change and combinational delay is equals to the final stable output. Both are important for correct circuit operation. Contamination delay tells when output starts changing, not when it becomes stable. Now that we understand both delays, let's compare contamination delay and combinational delay side by side. Now that we have understood both combinational delay and contamination delay, let's compare them. These two delays describe two different movements. In some signal transition, one tells us when output starts changing and the other tells us when output becomes fully stable. Contamination delay is the minimum time after which output starts changing, and combinational delay is the total time after which output becomes stable. One is the beginning and other is the end. Let's understand the nature. Contamination delay represents the earliest possible response of the circuit, and combinational delay represents the final response of the circuit. When input changes, output starts changing after contamination delay, but it is not stable yet. After some time, output settles to the correct value. That is combinational delay. Contamination delay shows when output begins to change, and combinational delay shows when it settles. In a circuit, there are multiple paths. Contaminational delay depends on the fastest path, the path with minimum delay, and combinational delay depends on the slowest path, the path with maximum delays. Fastest path versus the slowest path. These delays are used in different timing checks. Contamination delay is more important for hold time analysis because it tells how early data can change. And combinational delay is important for setup time analysis because it tells how late data can arrive. If contamination delay is too small, data changes too early, this can cause hold violation. If combinational delay too large, data arrives too late, this can cause setup violation. Let's summarize in simple way. Contamination delay is starts of output transition and combinational delay ends of output transition. Contamination delay tells when output starts changing, and combinational delay tells when it becomes stable. Now let's understand this concept visually. Using this waveform diagram, here we have two signals, input waveform on top and output waveform at the bottom. Let's start with the input transition. The input signal changes at the specific time. For example, from 0 to 1, this point acts as the reference point from where we measure all the delays. Now, observe the output. It does not change immediately. After a small delay, the output begins to change. This time is called contamination delay or TCD. TCD is the time from input changes to the start of output change. Now look carefully at the part. The output does not jump instantly to its final value. It gradually transitions, passing through an unstable region. This is called the output transition phase. After some time, the output reaches its correct and stable value. This total time from input changes to final stable output is called the combinational delay or TPD. TPD is the time from input change to stable output. Now, one very important relationship is TCD is always less than TPD, which means output starts changing first and becomes stable later. So this waveform clearly shows two things. Start of output change is contamination delay. End of output change is combinational delay. This concept is very important in real circuits because it helps us to analyze glitches or early transitions. Timing constraints like setup and hold. Early changes affect hold timing and final delay affects setup timing. Waveform shows when output starts changing and when it finally stabilizes. So this waveform, which explains both combinational delay and contaminational delay completely. Once you understand this, timing analysis becomes much easier. Now, let's move to the most important part, understanding how these delays behave in real circuits. In real digital circuit, both contamination delay and combinational delay exist together. They are not separate phenomena. They are two parts of the same single transition. When input changes, some paths in the circuit are very fast, so the output starts changing quickly. This early response is due to the contamination delay. It represents the fastest path in the circuit. But here is something very important. This early output is not always correct because different paths have different delays. The output may temporarily show wrong value. These temporarily changes are called glitches. Glitches happen before the output becomes stable. After some time, all paths settle and the output reaches the correct value. This time is defined by the combinational delay. It represents the slowest path in the circuit. In real circuits, there are multiple paths from input to output. Each path has different delay. So the fastest path is the contaminational delay and slowest path is the combinational delay. This difference in paths is the reason both delays exist. Now let's connect this to the flip-flop based system. If output changes too early, it can violate hold time. If output arrives too early, it can violate setup time. So both delays directly affect timing reliabilities. That's why in real VLSI design, engineers always consider both delays. They are used in static timing analysis, also called STA. Timing closures, reliable circuit design. Real circuits does not just delay signals. They produce early changes and final stable outputs. So once you understand this, you can early analyze any digital circuit timing and avoid timing violation in real designs. Now, let's understand why all of this actually matters. In real digital circuit design, data is transferred between flip-flops on every clock cycle. For correct operation, this data transfer must happen at the right time. And this is exactly where contamination delay and combinational delay become critical. Let's start with contamination delay. Contamination delay determines how early the output can start changing. If this delay is too small, data may change immediately after the clock edge and the receive flip-flop may capture incorrect data. This leads to a hold time violation. So contamination delay is very important because it ensures that data does not change too early. It protects the stability of previous data right after the clock edge. Contamination delay prevents early data corruption. Now let's talk about the combinational delay. Combinational delay determines how late the data can arrive before the next clock edge. If this delay is too large, data will not reach the flip-flop in time. This leads to a setup time violation. Now, here is a very important points which are combinational delay directly affects circuit speed. Higher delay means slower operation, lower delay means higher performance. Combinational delay limits the maximum operating frequency. So, for a circuit to work correctly, we must satisfy both conditions. That data should not change too early or data should not arrive too late. This balance ensures reliable operations. In real chip design, engineers use these delays in static timing analysis, timing verification, timing closures. This ensures the chip work correctly at high speed. Contamination delay protects against early errors and combinational delay limits overall speed. So once you understand this, you understand the foundation of timing analysis, which is one of the most important concept in VLSI. Thank you so much.